Hello everyone, welcome back to Wild to Learn. Previously, we were introduced to genetic algorithms and we finished all the tasks in that section of the game. And now we are moving on to a new epoch, and that one appears to be for neural networks. So let's go. Alright, let's do the code. Story, deep blue. Okay, we need more cats to collect data. You up for a party? Okay, the cat's getting recorded again. Ooh, I got more cats. Okay, I got more cats in the house, or maybe I borrowed some cats from friends, but they have now their emotions recognized. Cat emotions database. Okay, we're building a whole database, and we're using some kind of algorithm to detect their faces and their emotions. Okay, and our to-do list, the third one, improved cat emotion recognition with 2 eyes, is done. So continue. Next one, go recognize complex emotions, sarcasm and such. That is apparently done. So let's move on to perceptrons. Animal speech recognition, cat speech recognition, how to. Gotta admit, Dr. Coder was probably right. Probably right. This genetic algorithm is just too clumsy, especially now when I'm starting to work with speech recognition. Hey, come on, you haven't even waited for a year. Have some respect towards the natural selection, why don't you? Yeah, they've made a lot of improvements to perceptrons since old man Rosenblatt was around. Now they tend to join multiple perceptrons in big bad neural networks. Something like that could work for you, but don't forget gradient descent. It's like a life coach for your neurons. Helps them keep on the right track. Okay, maintain accuracy level. In certain tasks with perceptrons, you need to keep the accuracy of your data flow above the required level while the timer is filling. If the accuracy drops, the timer will be reset. The timer is only active in test run. Okay, so timer, you need to maintain 70% accuracy for 10 seconds, it seems like. Is that what it's saying? Okay, perceptron shape in the game, so we can classify shapes again. This is seems like the perceptron that we've seen before, or no. Okay, anyway, classifies shapes. While in training mode, the perceptron reduces the amount of errors trying to predict the shape of the elements. In test run, the perceptron only predicts colors. In the real world, unlike Rosenblatt's perceptron, present-day perceptrons can predict more complex nonlinear dependencies. Most common functions inside the perceptrons are tan, relu, and sigmoid. Okay, I have a feeling I kind of know what they are, but anyway, that's complicated. Math, integrals, derivatives, etc. Perceptrons are basic elements of each neural network. Okay, gradient descent. In the game, gradient descent increase error reducing speed. Yeah, see, this is a trade-off where you might increase error, but it what? Reducing speed, increase error? That seems like a terrible idea. I don't think the description is quite right, but anyway. Each element in the game has a small error fix value. This node increases this value. Not sure I understand. This node doesn't work in test run. In the real world, gradient descent is one of the basic algorithms which can train models, not only neural networks. Gradient descent calculates a gradient of all objects and steps closer to the target answer for the task. It takes a lot of time. I feel like it should be decrease error, but reduce speed or something like that. Anyway, we'll try it out. So perceptron shape. So let's just try doing this alone and see what it does. I have a feeling it's going to make you use gradient descent at some point, but I just want to see what this does and why it doesn't. Whoa. Okay, now it's 100% error. What is that? Maybe I put gradient descent in front? Okay, so now it's reducing the error. Okay, now it's at the minimum. So it seems like what gradient descent is doing is it's providing the information to train the perceptron. Otherwise, without that information, the perceptron doesn't know what it's doing and it's getting 100% error rate. Okay. So now that I'm not training anymore, I wonder if this works or if I still need to keep the gradient descent active. No, it seems like I don't need the gradient descent anymore after training. It was still maintaining its accuracy. So okay. I guess we'll do a few more missions to figure out how that really works. Gradient descent life coach for neural networks. Okay, classification of viruses. Mayday, a strange virus is killing people in Procyon City. We can't understand what type of virus is doing that. Please help. This message was sent to all programmers in the world. Okay, that's pretty wide. In the game, Perceptron color. Okay, same thing for colors. While in training mode, the Perceptron reduces the amount of errors trying to predict the color of the elements in test run. Perceptron only predicts colors. Okay, and this is the same thing. Okay, just the different colors, so we're gonna do the same thing we did before. Hook up the colors. Training. We'll wait until it gets to the minimum. Okay, and then it seems like now we don't need the gradient descent anymore. Let's just try that. Yep. Wait, hold on. Oh, okay. Yeah, okay. So I wasn't using that, but anyway, let's delete that. Okay, gold medal, yep. Perfect. Okay, we did get gold on that one, right? Okay. Alright. Perfect photo. Greetings, we represent the Phony Corporation. As you may know, we are producing all kinds of electronics, but we're especially proud with our photo and video cameras. We're currently looking to hire a programmer who could help us create a color chip, which could recognize colors and improve rendition with the least possible amount of mistakes. Please consider this message an official job offer to you. Okay. Oh, whoa. Jeez, that's... Okay, so we have to do the colors and shapes sorting again. Except this time we get almost perfect color sorting with just one node. So let's train the color thing first. Doesn't really matter what we connect the outputs to right now, we just need to train the perceptron. And then after this is trained, we're going to use this to sort out all the colors, and then we'll do the decision tree shape after that. Okay, so now we delete this. And then, oh, the red. Okay, yeah, it just needs to maintain the accuracy. It doesn't have specific requirements for what amount of objects it receives. So I'm going to put all the red over here because that's going to satisfy this. I'm going to put all the blue over here because it's going to satisfy all this. And then for green, we are going to need to sort the shapes. So I'm thinking, okay, it requires 80% accuracy, so that's we can't just do, so the simple approach is to put squares and half of the circles in here because we don't have a trash. We can't trash anything. And then triangles and half of the circles over here, but because of the numbers here, it's only going to get to 66% accuracy, not 80%. So that means we don't have enough, well, actually we have enough here because all the blue is correctly, all the blue is going to come over here. So the blue is going to help with the accuracy of green triangles. So the number of green circles we receive here is not going to affect the accuracy that much. This one though needs a little bit of help. So instead of putting all the reds over there, we're going to sort the reds a little bit. We're going to take all the circles and let's say half of the triangles and put them here. And then I'll change this to a square. So squares and half of the triangles go over here. So this one gets a little bit of help from red to dilute the number of green circles. I think that's gonna work. Wait. Oh, we're only allowed 2 nodes. Okay, that's kind of annoying. Alright, well, I think I found one way to do it. So the problem is we had to use a decision tree to sort the greens, and then we had to use a second decision tree just because we have too many of the green shapes that we don't want, and we need to dilute the error rate. So instead of doing that, I'm going to keep red distributed between these two, but all the greens, I'm just going to feed them right back here. And that's going to be a sort of pathological way to throw away all the greens. So the greens are just going to keep circulating in here. They're not going to go anywhere, which is kind of weird, but at least it's going to prevent any green from showing up at the output. So we're only going to get blues here and then some division of red items in the other 2 output streams. Yep. Yeah. The solution is kind of stupid. I'm not on board with how this works, and I'm not sure if that's the intended solution, but I couldn't think of a better solution. So this is what I thought of first, so I'm going with it. Neon City. Hello, our company Cyber Neon 2088 designs LED scoreboards. Each scoreboard is assembled by a robot, but then we have to spend a lot of time on quality assurance. We want to improve the firmware of our machines because it's ridiculous to have them in the first place if humans have to check after them anyway. It is necessary to distribute and solder the lamps of the desired shape and color to the places corresponding to the project plan. Okay, this is another one of those colors and shapes thing. We have a balancer this time, so that's going to make things faster. Gradient descent, perceptron, and decision tree, and we're allowed 4 nodes. Okay. So each one of these only needs about 50 to 60% accuracy, which is pretty decent. So I think the first thing I'm going to do is still to do the colors. I'm going to do a gradient descent just to train these. So that's the first thing we're going to do, just a little bit of training, and then after that I'll think about how to distribute the colors. Okay, so it seems like green and red are pretty obvious. There are ways to distribute green and red with just a decision tree. Blue is a big problem because blue only accepts squares. However, yeah, because the accuracy requirements are so low, I think we can mix in lots of the other blue items and that'll still be okay. So we're gonna put 3 decision trees. Alright, so I think we'll do green first because that's the one with the least requirement or the least conflicts. So it's easy to figure that out. We have green, we have circle and square. Circle with a mix of triangles, square with a mix of triangles. This should be good for green. Now the red, this one is harder to sort out, so we're going to use output stream 2 and 3. So that's square and circle. Squares go here with some triangles, circles go here with some triangles. And then blue, we're going to do, we're pretty much going to divide the squares evenly, but with a mix of other shapes. Also divide it evenly among the two. I think, I'm gonna test it. Okay, this one's not getting enough accuracy. Okay, so maybe, let's see, how about I only take squares and I take all the other, okay, actually that's going to make the accuracy even worse. So maybe connect all the blues over here, because even though there are lots of blue objects of an incorrect shape, we are also getting a large number of red and green items. So maybe that's going to even out the accuracy. Nope, doesn't look like it. Okay, fair enough. I'm gonna try the trick of just patholog. Oh, you know what? I actually have a trash can. Let's try that. So this one, the accuracy shouldn't be a problem. I'm just afraid it's going to be too slow. Nope, that's good. That's good. Alright, next one, Art Studio. Good afternoon. I'm a representative of the Assemble and Play Art Studio. We produce artisan goods, gaming, and sports merchandise along with other things. Among those are action figures, and those are quite complicated to manufacture. They consist of many small details, and here at A&P, we want our production to be just perfect. Therefore, we could use an algorithm that would help eradicate mistakes during production and painting of the details. Alright. More shape sorting, just what I love. Okay. So really? Seriously? 2 nodes? Okay. That's... Alright. Start with a Perceptron. Gonna train this. Doesn't matter how many sources we have, doesn't matter where we connect the output. This training bit is a little bit annoying because you have to do it repetitively. And it's always the same procedure, it doesn't really get you anywhere, so it's not that interesting. Okay. Alright, since we're only allowed 2 nodes, I'm thinking we pretty much have to merge these, because if we don't, then either we can't sort by color on one of them, or we can't sort by shapes, and we're gonna run very, very low. So I think we're gonna have to merge the inputs here. And then after we sort by color, I'm seeing green. All of the green can come over here. And then that takes care of this output. Red, all the red we can put in here. The accuracy requirement is only 40%, so we don't really care. The red shapes easily gets to 40% accuracy, and then for the blues, I'm going to do a decision tree to sort out squares. No, squares go here with some circles, and triangles go here with some circles. And I think that's as much as we can do with 2 nodes. Okay, perfect. Okay, let's move on to the next one. Oh, gradient descent. Oh yeah, we already have that. Okay. Error control. Or actually, yeah, let's do the startup, because that's on its own branch, and then we'll return to this one in the next episode. Okay, counter-terrorist system. Hello, we are creating a terrorism prevention system for crowded public spaces. Terrorists tend to carry parts of weapons on them. We have already digitized a large number of weapons and their parts, but we need an algorithm that could recognize them. Can you help us? Yes, but before that, I'm gonna save. Alright, now let's help them. Yep, 3,500. Holy. Okay. Okay, so I think we pretty much know what to do, right? Perceptron color is the fastest way to sort color. So we're gonna sort color. This is already trained, perfect. Okay, and then from previous experience, we know that not all of these need to be fulfilled. Okay, hold on. I have a... Okay, no. Yeah, I was thinking this one only requires 40% accuracy, so what if I just shove everything into this one? As I was saying before, from previous experience, we don't need to send outputs to all of these output streams because they don't have a quota for how many items you need to send. So we just need to sort colors into some of these correct streams, and that'll get us what we need. So this one requires 40% accuracy, so at least red and green are looking good. Red, I'm seeing 15, 15, and then green. Green, we actually want to filter out all the triangles. In fact, none of these accept green triangles. So do we have a trash? Yes, we do. Okay. So we'd want to filter out green triangles for sure. And then out of red, we can filter out, let's say, the squares to separate out from output stream number 1. So that's the job for a sift. This one takes a little bit less than 1 second. Random forest, I don't think, or isolation forest, I don't think will be super helpful here. And random forest is a little bit slower than the sift anyway, so we can use sift. Perceptron shape. Ooh, perceptron shape. Yeah. That's much faster than even sift, so yeah, let's use perceptron shape. It's much faster, and it sorts out all the shapes anyway. So circles, triangles. You know what? I'm actually going to be nicer and send outputs to a little bit better stuff. And squares go here. Okay. Trash can. Yeah, we still want the trash can, because for greens we want to throw away all the triangles. And then green squares go here because this one doesn't have an input yet. Green circles go here because this one doesn't have an input yet. Alright, and then blue, okay, perceptron shape. Circles go, let's say, go over here, squares go over here, and triangles, we'll send them over here. Okay, that's looking okay. Ooh, 95%. Yeah. So I'm seeing first of all, this one is absolutely terrible. What's happening here? Oh, okay. Because for the greens, there's only a tiny number of other shapes, but a huge number of triangles. So if our perceptron shape makes 9% errors, then yeah, we're receiving squares here. So even if, say, 9% of the 50 triangles come over here and mix with 3 green, it's still going to be overwhelming in terms of errors. So we're just going to throw this away because that's not reliable. And the green circles should be okay because it only requires 40% accuracy. Or was it? Now I am worried about the other ones because this one requires 100% accuracy, and we still have the same problem over here. Because we're using Perceptrons, all of them have an inherent error rate, so nothing's really going to satisfy our 100% accuracy. Maybe I'll just test this and see how it goes. If the error rate isn't too bad, I can still accept it, but yeah, this one is not exactly great. Right now it's about 70 or 80%. This one's doing barely okay. And then this one's not meeting a 95% accuracy either. Alright, so I thought about this for a while. So the main problem we were having is the accuracy rating, right? If we are to use Perceptron, which is faster, there's no way we can get 100% accuracy or even 95% accuracy. That's going to be very hard to achieve. We could also use, other tools, other nodes for 100% accuracy, but that's going to be much slower. So, because as mentioned earlier, we don't actually need to fulfill all the outputs, I'm thinking we want to primarily send our outputs to these low accuracy streams as much as possible. So we still start with the Perceptron color, and then after I filter by color, I think the reds, we can send them to this stream directly without any other processing. So it doesn't accept squares, but the number of squares is the same as the number of other shapes, and so we're going to achieve about 50% accuracy here, which is actually good enough, right? And then the greens, yes, the greens I also thought about because the vast majority of greens are going to be triangles, which are completely useless for us in the output stream. So instead of trying to process those, any way we want to process them, we're going to throw away the vast majority of them, and if we make any error here, then the green triangles is going to just completely tank our accuracy rating. So I don't think it's worth processing the greens at all. So I'm going to put this in the trash, and then blue. Blue is a little bit more interesting, so we need to separate out the circles. And for that, I'm going to use the Perceptron shape just for blue. The blue circles can go also into this low accuracy one, and then blue squares and triangles go here, even though, well, with 9% error, I think we're going to be a little bit worse than 95%, but as far as I can tell, this is the best we can do unless we add more nodes for, reprocessing and everything, but that's going to take more time to process. And so this is a simple way to get approximately that much. Actually, now that I think about it, green, yeah. The other issue I noticed was when we connected green to a Perceptron shape, even though Perceptron shape is relatively fast, because the vast majority of items is going to be green, so green has a lot more items than any other color, it was actually getting stuck. Processing was actually getting stuck at the green Perceptron. So that's another reason to just throw away all the greens, because throwing away is super fast, and it's not going to block processing of the other colors. So I'm going to test this. This accuracy I expect to come down a little bit lower. Yeah, now it's dipping below 95%. It's not super great, but I think I'm going to leave it like this. 40% accuracy is still doing okay. Or actually, you know what? Since we have the most squares and a small number of triangles, sending triangles over here may not be the best idea. Because again, if we have a small number of triangles and we make more mistakes up on the shapes over here, this is actually going to drag the accuracy down. So we're going to send the blue triangles over here, which only requires 50% accuracy. That should be better for the accuracy rating here. And then the 40 or 50% accuracy we don't really care about. We don't really care if they make plenty of mistakes there. And no, looks like it is not happy with the accuracy rating. Okay, well, anyway, it looks like the accuracy rating is holding. This one is just a little bit better than 50%. I don't know, let's try it with the triangles back up and see if that's any better. Yeah, I mean, it looks like the two are about the same. So yeah, maybe I'll just try this. Okay, next day. Yeah, at least we're making money. Our users, okay, we need a lot more users. So let's do the doubling with a balancer. That should get us more users. Yeah, next day. Made a little bit of money, yeah, significantly more income. We're still not covering all the users, but as I said before, I'm not going to double the processing again. So we're just gonna make this much money. Yeah, I know my solution probably isn't super optimal or super elegant or anything, but we're making significantly more money than our initial investment, so I'm gonna say that's okay. Okay, and then I'm looking for the day when the users drop low enough so that we can drop the balancing and move it back to just one lane. Okay, yep. Okay, we're at 6 out of 7, so we can afford to end this week with a positive income and then cash out. Okay. Great. We have some more stuff available in the C-Bay. Agitech Angry Tomato increases aim in games. It's a new mouse. It's cool. Nodes. Yes, we get the final node. Stochastic Gradient Descent. Works faster than gradient descent but may increase error rate. I don't know why works faster than gradient descent even matters because we're only using this during training. We're not using this node after training anyway, so the speed doesn't really matter. Anyway. Hardware, we get a handmade tambourine. That's a new tambourine, yay. Work node speed, data transfer speed, and a Xiaomu router increases data transfer speed. Alright. Yes, we can buy the other cat. Towel. Looks like a priest robe. Just a towel. Okay, I get it. Looks like a priest robe. Alright. This is all we have. And here's my fancy hair. Here's my new mouse. Here's the handmade tambourine. Here's my towel cat. Alright, I think that's it for this episode. I want to say more about gradient descent and everything, but I think I'll make that a separate episode or a separate video because I think there's a lot of interesting stuff to illustrate there, and it's hard to just talk about it. I'm going to try to do something visual. That's it for this episode. Thanks for watching. See you next time.